All right, so the next spectroscopy we're going over is fluorescence spectroscopy, also called emission spectroscopy, very closely related to UV visible spectroscopy. You're still shining the same wavelengths of light, so we're talking 300 nanometers to, let's say, 1100 nanometers, UV to the near infrared with the whole visible spectrum in between. And what you're doing here is taking advantage of certain molecules. So these have to be special type of molecules that undergo fluorescence. And so what you get from this is you're also detecting light out of the molecule. So you're doing the absorption experiment, but in addition, you're detecting the light coming out. Okay, so there's just an extra piece of equipment on the spectrometer to do this. And how this is happening, right, is let's say you have two electronic states here, one here, excited state, and then each of the electronic states, of course, has vibrational states within it that are closer in energy than the electronic states are separated from one another. And so you put light in, you pump it up to the excited state, and then you have some vibrational relaxation that occurs, and then you relax back down. And so you can see, because you have this vibrational relaxation that oftentimes occurs, the light that is emitted during this frequency, so this nu 2, okay, that is going to have a higher wavelength, okay, lower frequency, less energy than what you started at. So you might have, this is like a typical emission spectrum, right? You'll get the absorption part of it, the dye or whatever it is absorbs at around 350 nanometers, and then it emits at 550 nanometers. Higher wavelength light that it emitted at, most of the time that's what's going to happen just because of this diagram here. And so that is pretty much the essence of fluorescence spectroscopy. One kind of cool application of fluorescence spectroscopy, first thing I think of when I think of fluorescence spectroscopy is quantum dots. Okay, quantum dots are really cool because they are inorganic materials that are quantumly confined, meaning they're pretty small. So we're talking about nanoparticles, and because of that, they have very well-defined electronic states that you can excite them to. Not only are they well-defined, but they are tunable based upon the size or the composition, commonly the size. Okay, so you can shift the position at which the particles emit light, okay, based upon their size or composition. And so this is like particle in the box, guys, right? Like physical chemistry, you get a bigger particle in a box, you're gonna have less energy in that particle, right? So you're gonna be, as you get bigger box, you're going towards redder and redder colors. And you can get all colors of the rainbow. And what's nice is you get really sharp peaks a lot of times because these are really well-defined systems. And so companies like Samsung, all the state-of-the-art displays out there use really nice quantum dots in them. And they use all sorts of things. The first generation uses cadmium, then they try to get away from cadmium because cadmium is toxic. But you have these amazing displays, and I'm not a display guy or TV guy. I don't even own a TV, but I walked through Best Buy a couple times, and you look at these huge displays, and they're just amazing. And all this has to do with quantum dot technology and emission spectroscopy. So it's a really neat application, I think, of emission.